Alright, are we live? Let's see, so I'm gonna try to keep my voice low. As usual, I like to kind of talk low. Don't like to speak too loudly in general. You can set a timer for the amount of time that I want to sort of stream for. So hello and welcome. Hope everyone's doing well. I was looking at this problem the other day, and I got kind of stuck on it. And I just wanted to talk about it some more. So the deal is, I got really stuck on this question. I mean, I got like hard to fully appreciate how stuck I got. So usually I'll throw in the towel, throw in the flag if I get really stuck, and I actually feel really silly. I feel really silly about this question. I actually kind of want to. I'm gonna speak a little bit louder. Yeah, I'll speak a little bit louder because I could lower the volume somewhat. Let's just speak louder. It's because I don't really need to whisper right now. So I'm just kind of watching the volume meter moving and just also speak louder. So the thing that I'm missing is this is a hard question, challenging question. However, it wasn't beyond me. I would have taken me a very long time to figure it out if I kept thinking about it. It would have been a really long time. I don't know if I ever really would have on my own. So I have to admit that I took a peek at the answers, and there was one hint there. I tried not to look at the full answer. Oh man, it's so hard to talk properly. Hold on. I'm messing around with the audio, and all I see is the. Hold on, let me. I have the gain is up really high. Hopefully that fixes it. Okay, so the gain is up really high, and it's hard to like. I'm just watching this bar move that sort of gauges my audio, and I'm trying to keep it so that it's not too much. But anyway, so the deal is basically I looked at the answer. That's what I'm trying to say. I had all kinds of thoughts about how I could solve this problem. I wasn't really getting anywhere. Have to just kind of admit that I ended up using a hint from the answers, which I advise against doing that if you can. But if you're stuck on like for days and days and days, it's like, you know, sometimes you just don't know enough about the subject, and the best way to learn more about the subject is literally to look at answers to problems regarding that subject. So that's like the fastest way to learn more. And then you can think the next time you see that problem, you can have a sort of a different perspective and a possible way to see the answer. Yeah, this was hard. This is hard. I'm just thinking like how I could have arrived at the answer without getting this hint. And I'll explain the problem, I'll explain the answer, and what I implemented, and then I'll try to figure out like how could I have seen this previously, like how could I have done this without checking the answer. That's kind of the question I want to look at today, because the answer is really fast. Like this video would be like 2 minutes if I just like went right in the answer and explained it, but I kind of want to spend a little more time talking about it, because it's kind of a big deal if you can't think through an answer, or not an answer, but you can't think of a solution. That's kind of brutal. That's like you found a limit of some kind. All right, so let's just show that this is correct. Actually, I don't think I submitted it yet. I actually don't know if it's correct yet. I guess we'll do this together. Let's find out. It's not. Oh, that's awkward. Oh, no kidding. Uh-oh. Uh-oh. Ouch. Whoopsies. Whoopsies. Somebody made a boo-boo. I think you can still do this though. Hold on. I completely forgot about that. That's a more minor thing. That's not really. Oh, come on, man. No. Ouch. Ouch, 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 ouch. You can do something like this. Let me just see something here. Can we do this? We try. Oof. Oof. Hold on, this is a lot less clean. Not as clean as I would have liked it to be. I don't know if this is still correct. Oh, it is. Okay. Oh. Alright, let's just see how it goes. Got it. Alright. Oh, we're not 100%, but we're pretty fast. We're pretty good. No kidding, really. Ouch. Well, you can do this. I wonder if you did this way. That still works. I'll explain. Explain the whole solution here. Alright. Oh, can't believe I did that. That's so silly. I'm not sure if this is any better, quite frankly, than yeah, that's really super awkward. Alright, I'll explain what the solution is and what happened, and no kidding. Wow. Brother. I wonder if it's faster. Hold on, let me see. Hold on a second. Something like this. Not much faster. Okay, anyway. I will explain. Okay. Mistakes. Sorry, mistakes. Okay, so given an integer array nums in which exactly two elements appear only once and all of the other elements appear exactly twice, find the two elements that appear only once. You can return the answer in any order. Follow up, your algorithm should run in linear runtime complexity. Could you implement it using only constant space complexity? And so example, you have 1, 2, 1, 3, 2, 5. The output is 3 and 5. 5 and 3 is also a valid answer. Negative 1, 0. Would just be negative 1, 0. 0, 1 would just be 1, 0. Every integer is going to appear twice. Only two integers appear once, and you get bounds on what numbers will be present, and how many, how big our array is going to be. So I think I showed before that the answer that I had before was basically create a frequency map. Just count how many times you see each number, and then print only the number, or return only the numbers that have that only show up once, and then you're done. That's it. Super straightforward. That, however, uses a bit of memory to do that, considerable amount. This is a very clever way to use bit manipulation I'm going to show you to avoid using that hash map, avoid creating a frequency map. So what this does is this takes this integer alpha, we'll call it, and we take the XOR of every number in our array, which I think I described earlier is this basically you have sort of, if you have A and you have B and you have A XOR B, it looks like the following picture. If I could draw this properly. I'm not too artistic today. So it would look like the following: 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. This is basically the truth table for A XOR B. What's neat about this is anywhere A and B are both 0, you have 0, and anywhere they're both the same value. Basically, anywhere they're the same value, this will come up 0, and everywhere they're different, it'll come up 1. And the neat property about this is if you chain XORs over integers, if you see two integers and you XOR them with each other, that gives you 0. And 0 XOR some other integer is just going to be that integer. Which means that if you chain a whole bunch of XORs over a whole bunch of numbers, if there's an even number of them, let's say there's 2, so in our case we have a whole bunch of 2s, pairs of numbers, duplicate numbers, those all disappear out of the XOR chain. And actually the two numbers that are left, the two numbers that aren't duplicated, the ones that are unique, those will be the results. You'll end up with this sort of, if you let the first number be A and the second number be B, XORing everything will give you this sort of a expression, or this kind of a you get a number represented by basically it'll basically be the XOR of those two numbers. Now keep that in mind. That's we're going to make use of that. So by the way, because of that, if you found either A or B and you XOR it with that result that we got, it'll give you the other one. So if A XORed with A XOR B will make A disappear and it'll just be left with B. B XORed with A XOR B will make the B's disappear and give you just A. So you can kind of use that to find out the, you can basically use that if you find one of the values, you can then use this to get the other value, which is exactly what we're going to do. Now what you do, which is really neat, is the resulting number, once you do that, that XOR everything across, it's sort of a bit mask, and all of the ones and zeros, all the zeros obviously we don't really care about, but the ones are important to us because those ones, those bit positions, right, the integer is just a list of zeros and ones. Those 1 and 0 position values that we're interested in, every one of those is only going to be owned by either integer A or integer B, but not both. And it must be owned by one or the other, right? That's sort of the property. Which means you can actually segment these bits into, you can sort of split these bits into two sets of bits, where this is the set of bits that belong to, or bit positions that belong to A, and this is the set of bit positions that belong to B. Now I wouldn't say you could split it, but you could conceptually understand that there are these two separate sets. I wouldn't say you could necessarily find those sets, but you know that they exist. You know that there are these two different sets. And a bit that belongs to one set doesn't belong to the other set. Now what's really neat about this is that because we're considering only that bit, all of the numbers that have that bit, the set of numbers, so we could actually consider this, we could split now this list of numbers into two separate categories. If we just pick one random bit from one of these sets, we can split into two categories because we know all the numbers that contain that particular bit that we just grabbed, that we know is in either A or B. We know that bit isn't present in B. And we know that all the numbers where that bit is present it's either in A or it's in some other number, and it's not in B, and all the other numbers, that bit's going to be present twice. So if we take that bit and we basically mask, we basically say we're only going to consider the numbers here that contain that bit, that actually gives us a partition of, it actually partitions our set into two pieces where we have a whole bunch of duplicated numbers, A, and then the other partition is all the numbers that don't contain that bit, so it's a whole bunch of duplicated numbers, and B. So now we have actually we actually can use that to create a partition, create a partition on our numbers that we know there's only one unique number in there, and that unique number is exactly, I guess we'll call it A. But obviously there's some, you can name A and B whatever you want, obviously if it's, well, yeah, we'll do it that way. Let's express it that way. Just express it as I've expressed it. It gets a little confusing because you could be like, well, all of these bits belong to A, all these bits belong to B. Well, you could swap that and just say all these bits belong to B, all these bits belong to A. We'll just say vaguely that we're going to grab a bit and then call the set that it belongs to, call that A. It's group A. So now what I was saying before about you can use the XOR function to get rid of all of these other duplicated values. Now once you've masked this partition, so you have a set that contains A, and all the other numbers that are in there are also only duplicated numbers, that those doubles. Now you can perform the same bit mask operation again to just get A, the same XOR, not bit mask, the same XOR operation. So that's what happens here, is that basically you just do pretty much the same routine, except this time you say only if this bit is present on this number are we going to consider this number. So that way you're sort of only operating on that partition of the set, and that'll give you the first number. And now the really neat thing from there is, by the way, there's a little bit of bit manipulation here to get that particular bit. How we actually choose that bit is kind of nifty, but I'll explain that in a minute. But then we get that first number, and then what I was saying before is, well, this XOR that we calculated before actually gives us A XOR B, and now we just got A, now we can use A and A XOR B to just get B. And that's using XOR one time here, and that gives us the number. Now there's a little bit of funky stuff going on with using long numbers, long integers, and the reason for that is basically the math that I do here. It's a little bit, it's not really math, I'll explain what this does, but this subtracts a number off, and the problem is that this thing could potentially be the bottom of the range of acceptable values for integers, and then if you subtract 1 you go off the bottom, and that causes an error, like an internal error in the program, and so yeah, that's that was the runtime error that I ran into, which is kind of embarrassing because I always forget that, but yeah, that was a test case where that happened. And so what this is doing is this is just saying, okay, it's all the same logic, but we need a larger container so that we can actually make that subtraction, and then so basically promote everything to a larger container, perform the you can actually do this, you can even do you can do something like this. This shouldn't be. Can you do this? And then put the result in a smaller container. Does that work? That's the problem. Okay. All right, that's better. That's a little cleaner. Yeah, we just need a larger sort of container for our bits, and then put the results pretty much always going to fit into a smaller container. So that's really all that was going on here. That's all you need to do. So that way you can actually subtract 1 and go through that bound. So So I explained this part, but I didn't really explain this part. How do we actually select the bit that we know? We just need any one of the bits works in this case. So we just need to pick a bit that's in this alpha, we call it alpha, which is that A XOR B result. And you can take any bit, doesn't matter. What this does is it's kind of a nifty little trick that you do, bit manipulation trick. But what this is doing is if you look from right to left on like a bunch of zeros and ones, any particular integer from right to left, there's a sequence of zero or more zeros, and then a 1, always, unless your number is absolute 0, unless alpha is actually equal to 0, which I don't know if that's possible. I don't think it's actually possible for alpha to be 0 in this case. It could be. There's no bits. I don't think so. The only way it could be absolute 0 is if both A and B are the only way it could be 0 is if A and B are both zero, because there has to be no bits contributed by A and no bits contributed by B. Or if if A and B both contribute all ones, I want to say. So if they're equal, I think if they're equal to each other, this could be 0. But obviously we know they're not equal to each other. Other cases where if they're not equal to each other, that means there's some bit that's in A, for some bit position where A contains that bit and B doesn't contain that bit. Right, being equal means all the bits are the same. So by definition, the XOR can't be empty if they're not the same. Yeah, okay, that's what I need to know. So we know it's never going to be equal to 0. So there is some bit to find. And basically, if you can guarantee that there's a bit, then you'll have a sequence of zeros and then a bit, a 1. And if you subtract 1, what happens is all those bits those zeros flip to a 1, and where the 1 was flips to a 0. And we're going to forget about nothing changes to the left side either. So nothing to the left of that changes. That position goes from a 1 to a 0, and all the zeros to the right go to 1, and then so that's when you subtract 1. Now, if you flip all of those bits, all the bits that were 1s become zeros, back to 0. The 0 that flipped to a 1 goes back to a 1, so basically you go back to what you had before. However, all the bits to the left side all get flipped. That's what this does. This is a negation. This flips all the bits. So what happens is you actually end up with all the same zeros, that same 1, but everything to the left side is flipped to the opposite value. And now when you AND that result with the original value, because all those bits on the left side that got flipped, those all go to 0. That 1 and 1 is still 1. 1 and 1 is 1, and all the zeros to the right are all still zeros because they're all zeros ended with zeros. So you end up with just that 1 bit in that first position, which is great, which is exactly what you want. And the reason why we want to do that is it's a 1 in a certain position. That's sort of the bit that we want, and then zeros everywhere else. If we AND that with a particular number, there's only 2 options. It's either that number has a bit set in that position, and therefore that's a non-zero number, or there's no bit set in that position and it's just 0. Right? You only have 2 options. Either that bit is set or not set if you AND sort of that mask with a particular integer, which is exactly what we do here. So that allows us to filter all the numbers that don't contain that bit, or in this case we want all the numbers that do contain that bit. And then if you XOR all those numbers, do we get the first number that we want, because that set contains the number we're after, and then any number it also contains is going to be duplicated, because we know all the other numbers are duplicated, and we know that B is not in that group. So really clever, really slick, really clever. I really like this question. I really like the answer. I feel like a genius. Just for understanding how to do that. Makes me feel so smart. Yeah, kind of grateful I got the opportunity to kind of use a little bit of bit manipulation knowledge with the XOR function and bit masks. And a little disappointed in myself though, because I'm wondering if I could have thought of this myself. I don't think so. I don't think I ever would have thought of that, to actually find a way. I was considering somehow that there was a way to partition the numbers into one partition that contains the number we're looking for, another partition that doesn't contain it. I did not consider that I could actually use bit manipulation to create that partition. That's really clever. That's like a really clever approach here that was used. But yeah, I don't know. I didn't think to do it that way. I didn't see it. I'll have to remember that in the future, that you can actually use whether or not a bit is set to partition numbers if needed. I guess that's what I have to remember in the future. I mean, I knew you could do that in theory, but I've never done it before. And the reason you would do that is because you know that any bit that you grab from this alpha, it can only belong to either A or B. So a mask that contains that bit will not contain B or will not contain A. Right? It only contains one or the other. And you can just say, just give me all the numbers that have that bit, and exclude all the numbers that don't have that bit, and then boom, you've got your partition that contains one duplicate and doesn't contain the other duplicate, and then you get XOR everything, and then you're in good shape. So interesting, such an interesting problem. That's pretty wild, A little disappointed that I haven't got 100% though on this. I wondering if there's a way to do this that's a little more clever, a little faster. I don't think so. I think it's kind of as fast as it gets. There might be something that just uses a little bit less computation. Because this goes through it twice, makes 2 passes. I'm wondering if there's a way to do this where it doesn't use 2 passes. Just thinking. I don't know. There's like a little bit of extra computation for moving this to a larger, like a register, I guess, or larger container. I'm just thinking like how I think I'll just be satisfied with it as it is, and it's pretty good. That's pretty good as it is. I think that's enough. We got the idea. I don't need to go crazy here. Would be nice if there was a way I could. Right, there's one solution that's 0 milliseconds, even faster. So. There are other solutions in the discussions, so maybe I could probably look at those to find out what was done. But just thinking if there's like a way to make this a little faster. No, I'll just leave it as that's fine. I mean, that's good enough. It's really a little bit excessive to go further than this. All right, so yeah, so that's the solution. You know, sort of the constant space-time complexity version of it. I don't know how I could do this with, like, if it said find 3 elements that appear only once or something, you know, like, I don't know. These questions are always fun, but they always make my head hurt because they seem so specific to the problem, I guess. Like if there were 3 elements, then I'd run into some issues because my XOR would no longer be, I would no longer be able to know. I wouldn't be able to do this, certainly not, where I could just grab a bit and say, oh, use this bit to figure out, you know, to partition the set. It would belong to, so that's actually a good question. Does that still have the same property if you XOR with 3 different numbers? I wonder. Do a little bit of bonus exercise here. Let's use this guy. This is a little more sane for me, I think. Bit of a bonus. So we got 1, 2. We want 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Is that it? 1, 2, 3, 4, 5, 6, 7, 8. Okay. We'll do 0, 0, 0, 1, 0, 0, 0. These are all going to be zeros. 1, 2, 3. The first 4. These are all going to be 1s. I could do it this way. This is going to be 0, 0, 1, 1. This is 0, 0, 1, 1. And then these flip between the 2. It's just from all those years of drawing these things. I think it's got to be just one thing that has it. That bit. I think it actually does work. No. Because you have this situation. So what happens is, obviously all the zeros go to 0. So yeah, this is a 0 and a 1 is a 1. 0, 1, 1, 1, 0, yeah, 1. This goes to a 1 and a 1 is 0. This goes to a 1. This goes to a 0. Right, so there's potentially in all 3, A, B, and C, or it's only in A or B or C. So here's the question. How do we find a bit that's not in all 3? Like how do we test that the bit's not in all 3? We just want to find the bit in one of them. And then if we could find the bit in one of them, then we can partition our set in such a way where we can actually apply the same logic that we just applied to sort of figure out the two elements in the other partition, right? We could sort of write a mask for the other partition, and then and we're in good shape. But how do we make sure that the bit we grab is not in all three sets, A, B, and C? Actually, I think what you could do, well, what if, okay, there must be one bit, because A, B, and C are different from each other, there must be at least one bit that's not in all three. So what you would do is you would test each bit, and if the mask gives you the whole set, in other words, all the numbers, so you do a count, if all the numbers oh no, that's not really correct either. No, there's no real way of knowing. No. Oh, no kidding. Wow. Well, okay, I got it. This is perhaps one way of doing it. For each bit, you're going to perform. Actually, you'll end up doing it directly then if you do it that way. For each of these bits, there's 32 possible bits. At most 32 bits. I think it's probably going to have to be less than that, some number less, but at most 32. You would actually directly find for each bit what the result of that mask would be, and you'd get a whole bunch of different numbers. You get actually 4 different numbers. You get A, B, C, and A XOR B XOR C. Pretty much, I guess what you could do is just you could just loop through each bit, and until you find something that's different from A XOR B XOR C, because obviously if you just XOR everything, you get A XOR B XOR C. So as soon as you get something different from that, then you call that one A, and then you're in good shape from there. But if you keep getting this number over and over again, then you if you keep getting that number over and over again, then you then those bits are actually bits that are present in A, B, and C, which is possible, right? That sort of intersection over all three. Pretty neat. So there is a way to modify this too for also the 3 case, but now you might get more complicated and say, what about the four numbers case, with A, B, C, and D, and then things start to get a little funky. You probably want an operator that, I mean, you could probably still keep abusing the XOR operator realistically. Actually, you could probably, because you really do end up with only 32 different numbers each time you run these sort of operators, and you probably can figure out which one's which, so something like that. I guess, I don't know if you used more than just one number. I mean, more than 3, more than 4, if you kept increasing the number of non-duplicated numbers, non-duplicated values, or non-paired values. Very interesting question. Very interesting question. Learned a little bit more about bit manipulation today, so that was fun. That's interesting. Yeah, bit manipulation is quite the thing. Quite the thing. All right, so that'll be it for this video. Thank you all for watching. Appreciate it. I realized that was like 40 minutes. We're talking about the bits, talking about bit manipulation for 40 minutes. Yeah, that's always fun. Let me go ahead and I'll end the stream, and I think I'll take like a few minutes to just like relax, and then I'll pick up the next problem, and we'll see how quickly we can go through that one. So thank you for watching.